Hello students, it is nice to once again come back to the last part of gravitation chapter. Hope you're all fine, and I hope that you would have watched my previous video of escape velocity. So today we are going to see about orbital speed and period of revolution of satellite. When you talk about orbital speed, you can also say this as orbital velocity. It is given on page number 498. You can turn to page number 498 in your book, and this is orbital velocity. Before getting into the point of orbital velocity, I'd like to give a quick recap on what we did about the velocities. Whenever a rocket going up above the surface of Earth, that there is a need of two kind of velocities. One is escape velocity, next one is orbital velocity. What is escape velocity? The velocity which is needed that this body will escape the gravitational pull of the Earth. So this is a planet here. It is going above. So you need to definitely have a minimum velocity to escape the gravitational pull so that this will not come back. So we saw this derivation. We found this as a final formula for escape velocity. VE it's also be equal to 2 times of GRE square upon RE, because GM means GM is going to be equal to GR square. We already know this one. So here it gets cancelled out. So 2GR. So that's what we saw, and we saw escape velocity is going to be equal to, what is the value? 11.2 kilometers per second. So that's what we saw. So very high velocity it is needed to escape the gravitational pull. This is a minimum velocity. If you want to give more than this, it's up to you. You cannot give below than this. Now we are going to see orbital velocity. Now that satellite has gone above, so it usually takes a trajectory. It usually takes a trajectory like it just makes a kind of a curve and then goes. So as it has reached that point, then and at the end of the time, you have to give a final push for the satellite to go around the Earth in an orbit. So the push that it has been given, the minimum velocity given to the satellite or to the body to move in the circular orbit is called orbital velocity. So we are going to see about orbital velocity, right? So you can write down orbital velocity. So you can write down the definition first of all. What is the definition? Yeah, you can go ahead and write this definition. The velocity required to be given to the satellite after reaching a height above the surface of Earth so that it can revolve around the Earth in its own orbit is called orbital velocity. You can draw this diagram now. Leave some space, leave the space, and then draw this diagram. This is Earth. So in this one, we take a height above the surface of Earth, and this entire thing we need to make this as the orbit. So if this is the height above the surface of Earth and this is the radius of the Earth, so this body is given an orbital velocity. This is mass m, this is mass of the Earth. So we find there is definitely a velocity which is needed after it goes to the top. Now we are going to see how this velocity appears and in what way it revolves around the Earth. there are so many beautiful facts you will be deriving it. So you need to be very alert and see it as an interesting manner. For example, you are able to watch the cricket match. Where is the cricket match happening now? IPL. You see the cricket match is happening somewhere in Sharjah and then in Abu Dhabi. But we are able to see it here. How is it possible? What's happening there? So there are geostationary satellites sitting in the top, and they are taking the information and they are able to give it telecast in the live. Any part of the world you will be able to see it live because of the geostationary satellite. How high is the geostationary satellite? That we need to see. We also know about a remote sensing satellite. It will capture the picture, Google Maps. You can see Google Map, you can see even how much is the traffic in some of the roads. That is all very clear. How they are able to do? That is because there is a remote sensing satellite. It will do the images of the entire earth and then it will give it to you. So quite interesting. So we are going to start now. Right? Consider a satellite of mass m above the surface of earth in a height h. The force of attraction between the satellite, the force of attraction between the satellite and the earth is given by force F is going to be equal to G into mass of the earth into mass of the satellite upon the distance here. So we can say distance is r square. What is r distance? We call it as a distance from the center of earth till this point here. This is r square. That is a force. G-M-E m upon r square. The next line is, once this is a force which has been experienced by this body because there is a force of attraction here. Then the next one is the centripetal force. Centripetal force given to rotate in the orbit. You know what is centripetal force? mv square by r, mv naught square by r. What is v naught? V naught is the orbital velocity. Now it is already going now. It is going around the orbit. You have to give a velocity here. And the velocity, because of the velocity, it will go around it. And which is contributing to the centripetal force. How you got the centripetal force? Because of the force of attraction. It will not allow it to go hayway here and there. There is a force still pulling it. Whatever the lighter body or bigger body, it will keep pulling it. Look at the moon. Moon is such a heavy body, so huge. Still earth is pulling it and keeping it on track. So the force will be keep on having it so that the earth will not allow it to go beyond this orbit, but it does not come back to the earth. That is the reason escape velocity is there. So orbital velocity is still there to keep it on loop, because and that is a centripetal velocity, and there is a centripetal force, and then there is a gravitational force which is contributing to this. Equating the forces, what you get here, G-M-E-M upon r square is going to be equal to M-V naught square upon r. Now remember, what is r? R is, what is this r? It is from the center of this earth till the top point. That is called r. In other words, this r could be also equal to Re plus height. Re plus height. That is what the total thing is. Now, some of the things can get cancelled out. R and r square also gets cancelled out. So you get here only V naught is going to be equal to, V naught square is going to be equal to G-M-E upon r. So what is V naught is going to be equal to under root of G-M-E upon r. So V naught is going to be equal to GME upon, what is this R? This R is RE plus height. So this is a very, very important conclusion. You can say this is equation number 1. The velocity of orbital velocity, orbital velocity V0, it is given as GME upon RE plus H. So that is already given here. Now you can also change this GME into some other thing also, which we know already. GME is going to be equal to GR square. Since how this one came? So G is going to be equal to GM upon R square. So this is the basic thing. So you can cross multiply this one. GM is equal to GR square. So we can remove this GM and put here as GR square. GRE square upon RE plus H. So V0 is going to be equal to RE under root of, this RE has come out of the square root. So G upon RE plus H. This is also 1A. Same format, little different. Okay. So this is the second format of getting this particular thing. Now we can again find out what is the minimum value of the orbital velocity. For example, if this body is already going in and above a good height, then there is orbital velocity. What if it is very close to the surface of Earth? Let us try to find out if it is a satellite which is close to the surface of Earth. When a satellite is close to Earth, then height is less than RE. This height will be very, very less. Suppose if it is only here, then very small height is there. It will be very small when compared to the radius of this Earth. So what can you do? Neglect the height. You can neglect the height in this formula. V0 is going to be equal to RE under root of G upon RE. What happened to height? We are just taking it away because it is very small value. It is already 6400 kilometers. If you have only certain hundred of meters or maybe 1000 meters, it is very, very less. So you can remove it. Now bringing this one inside, which is going to be equal to under root of G into RE. That is V0. That is another format of weighing thing. Now look at this one. We already seen 3 different format. This format is when for the height which is very, very less. Now we can also substitute the values and then get this answer. So if you try to put the value here, so what is V0? It's going to be equal to under root of GRE. It's going to be equal to 9.8 into 6.4 into 10 to the power of 6. Alright, meters under root. So V0, now if you substitute this value, you will get 7.9 into 10 to the power of 3 meter per second. That is V0. In other words, 7.9 kilometers per second. That is V0. So the minimum orbital speed around the Earth, surface of Earth in the orbit is 7.9 kilometers per second. Now look at this one. It's a very, very high speed. Within 10 seconds it will go to 79 kilometers within 10 seconds. So it is quite fast. So you can cover up a lot. So in this speed. So when you look at a satellite going around, it is going in a very, very high speed. Your entire things has to be very much intact. Otherwise it will all fly away. Your screw and everything will just loosen it up and it will go away. Because it is going, look at the speed. The speed is very high. So that's the way in which we see as an orbital velocity. Now there are 3 other format we need to explain here. So there is first part is first part is velocity. So velocity we have already derived now. Second part is the time period. Third part is mass of Earth. Fourth part is we are going to see the height of orbit. These are the 4 subdivisions we need to do. We have done only this much. The other 3 is still left out. Whenever they are asking the question, they might say derive orbital velocity and derive this one, or derive only the height. They can ask anything. But there are 4 subdivisions here. Okay, please write down the 4 subdivisions just below this topic itself. It will be quite clear for you. Now, we are going to go to the second part of it. What is time period means? Time taken to go around this whole thing and come back. That is called time period. So it can be quite fast. It can be quite slow also. Moon is also there. Moon is taking 27 point some days to go around. To an extent 28 days. That is a lunar orbit. So the time period of moon is 27 days some hours. So that is the orbital time it takes to go around. There could be some satellites will go exactly 24 hours. It starts here and goes within 24 hours, it will come back to the same thing. Same as the rotation of the Earth. Earth also rotates in 24 hours. It just goes around. This also will go in 24 hours. Exactly. That is the time period. So it depends upon how much height you keep. So we are going to see these all 3 quite similar. If you know this one, these 2 are very much easy. Don't worry about it. There are many things is not there. It is pretty similar. Okay. So let's start now. So we are going to see about time period of revolution. So what is the time period of revolution? Please write down the time taken to revolve around the Earth for one full rotation. To revolve one full rotation is called the time period. So time period is going to be equal to one full rotation is 2 pi r upon v naught. What is this one? Circumference. So circumference of the orbit and velocity. Distance upon, it is called distance upon velocity. That is time period. What is the distance? It goes around the whole orbit. So Earth is here. This is the r value. So this whole thing is 2 pi r, the distance, divided by the velocity. Now this is going to be equal to, time period is going to be equal to 2 pi r divided by, now you need to put the velocity here. So what is the velocity here? Orbital velocity. Do you remember this one? What have we derived earlier? So you should know it is going to be equal to under root of gm upon r. That was the derivation that we derived. In other words, this r is going to be equal to re plus h we had. So you can write down, it is going to be gme upon r. What is this r? From the center till this point, it is capital R plus h. So this is equal to, do the reciprocal, 2 pi r under root of small r upon gme. Now this r can be put inside, 2 pi into r cube. When this r goes inside, it will become r cube, because this is already r square will go inside, upon gme. Now we are just on the last part of this format. Is going to be equal to, what is r? Re plus height, the whole cube, divided by gme. So this is that time period of revolution. Please remember this particular formula. This is formula number 2, the second formula. Already we know gm, also we can take it as gr square is going to be equal to gme. So time period is can also be written as re plus h the whole cube upon gre square. Alright. So this is also a format of another format of formula. Okay. Now we need to little more see carefully what are the variables here, whether everything is similar. So we wanted to make sure the time period is depending on what factor the time period depends upon. So let us try to make the mass of the earth is going to be equal to volume into density, which is equal to 4 by 3 pi r cube into density. So in this place, remove mass and put this value. So we are going to see here time period is going to be equal to 2 pi into under root of Re plus h the whole cube upon 4 by 3 pi r cube into rho. And G is already there. The G is there. Re plus h is same thing is here. And 2 pi is the same thing here. One thing is we are going to put volume into density. Now this 2 pi you can bring it inside and then you can find the final thing. 4 pi square it will become Re plus h the whole cube divided by G 4 pi r cube rho. This 3 you can bring it up there, so it will become 3 into. Right, now 4 pi, 4 and 1 pi it gets cancelled. Rest everything remains same. So this is Re. So what is final thing? 3 pi Re plus h the whole cube upon G Re cube into rho. This is the time period. This is another format of the same formula. This is the first format, GME. Second format is GR square. Third format is instead of the mass, you're putting the density. Look at this very carefully. So all of them are constant. 3 is a constant, pi is a constant, G is a constant, the radius of the earth is constant, everything is constant. Since all the values are constant, what is except the value of height? Therefore time period depends, T depends on only height. The time period of revolution around the earth, it depends only on the height of this orbit. Whatever the height it is. So time period depends only on the height, not on any other factor. More the height, accordingly the time period will change. So time period depends only on the height of the orbit. Okay. Now you are going to do little more some of the things we'll try to see how this time period is going to be there for many other things. Let me take this particular format and I'm going to just do a small thing for a satellite, close to Earth. So height is less than Re, very very small. So I'm going to take this formula. So T is going to be equal to 2 pi into under root of Re plus h the whole cube upon G Re square. This is what the formula we already know. Now look at this one. Height is very small. Neglecting height. So this height you just remove it. What is the formula then? 2 pi into under root of Re cube. This is Re cube upon G Re square. So this one get cancelled, this one get cancelled, then you get Re upon G. It is just Re upon G and 2 pi. So T is going to be equal to 2 pi into under root of Re upon G. What is this formula is for? For a small height. for a very small height. If you want to substitute the value here, t is going to be equal to 2 pi into under root of 6.4 into 10 to the power of 6 upon 9.8. When you substitute this value, and then finally you will get this answer as 84 minutes you will get. You will get it as 84 minutes. So what is this new format you are getting here? When the satellite is very close to the surface of Earth, deleting or neglecting the height, the nearest possible part, for example, this is Earth, and you find an orbit very, very close, the nearest possible part, the height very close to the surface of Earth, still it has escaped the pull. It has escaped the pull. It's the nearest. It starts from here, it goes and comes back in 84 minutes. This is a minimum. What does it mean by that? Within 90 minutes, 1.5 hours, the satellite goes and comes back. What a speed it is. Can you imagine traveling the whole round the Earth in 90 minutes? Impossible. But the satellite does it. It is there in free space. There is no resistance. There is no route. It just goes quickly done. In meanwhile, when it is traveling in such a high speed, they used to keep this kind of a satellite for trying to take pictures of the entire of the Earth. So it will keep on revolving continuously. In a day's time itself, it is going to go around at least 15-16 times. So you'll be able to keep on seeing various variations, what is happening, weather monitoring, as well as the cloud control, flood relief, and even tremors and many other things, forest fires, everything this will capture. Traffic it will capture, these satellites. So it could be more of a remote sensing satellite, trying to sense everything on the Earth. It will capture pictures. So that is the kind of a thing you will be able to see out of the satellite which is here. So hope you got this idea about how this one works. Right. So now we'll again go back to this particular part. Velocity is done. Time period is done. Now we are going to see the mass of the Earth. So look at this format itself. Look at this format. You get the first formula that you have derived. That is very important. Time period is going to be equal to 2 pi into Re plus H the whole cube. This is 1. Take the same value itself. So the third part of it is mass. To find mass of Earth. How you can find the mass of the Earth? Everybody will say how can you find it? You cannot put in a physical balance and find out. A satellite which is sent above, it will do that job. Come on, how it is possible? Look at this formula. T is going to be equal to 2 pi into under root of Re plus H the whole cube upon G ME. We know time period of the satellite around the Earth. Satellite around Earth. We know the time period of the satellite on the Earth, T is going to be equal to this much. Squaring on both sides. T square is going to be equal to 4 pi square. What will happen to this one? The root will go away. Re plus H the whole cube upon GME. Now what do you wanted to find out? To find the mass of the Earth. This is the mass of the Earth. Cross multiply. Bring this one down. ME is going to be equal to 4 pi square Re plus H the whole cube upon G into T square. This is the value. Very simple. There is nothing much we have done. Same formula we have put. M we have taken here. T we have brought it down. That's all. So if this is the value here, I already told that is taking 84 minutes. We already know how much height it is. If you know the height, if you put this one in a particular height, and in that height how much time it revolves around the Earth, If these two parameters are known, rest everything is constant. Put this value, you will get the mass of the Earth. You can put multiple satellites and keep on referring what is the mass of the Earth today. Is it shrinking? Is the mass getting less, more? Everything you will know, because in that particular mass the orbit also will be there. So please be clear with this concept, how this one works. The next thing is, now look at, we'll go back to the thing. This is done. Mass of the Earth is done very fast. Height of the orbit. This is also very simple, but it has a lot of meaning in it. Height of the orbit. So this is the fourth part we are going to see. Right? So write down height of the orbit. How will you find the height of the orbit? In what height it is going? Same formula you can take. Either take this formula or either take this formula. In the height, it will be better if you have small g value, because for numerical sense. So we are not doing the second part of it, we are taking second A. Both are same. So write down, we know the time period of revolution is t is going to be equal to 2 pi under root of re plus h the whole cube upon GRE square. Right? This is the formula. Now what you need to find out is very simple. You can do it yourself. You need to bring this height here. The rest everything should be here. That's all. Same formula. Nothing much. Can you do that? Pass this one and try to do square on both sides. After squaring on both sides, this root will go away. Then you need to bring this height this side. Okay. So I'm doing it now. If you want, you can pass it and try to do it yourself and then release the pass and see how it is done. Squaring on both sides. T square is going to be equal to 4 pi square Re plus H the whole cube upon G Re square. So Re plus H the whole cube, keep it here, rest everything goes here. So it is T square into GRE square upon 4 pi square. Now what you need to do, Re plus H is going to be equal to, take this root here. So this whole value will become 1 by 3. This 3 when it goes here, T square G Re square upon 4 pi square. So what is the height now? We are close to the answer. Bring this Re next side. So it is going to be T square G Re square upon 4 pi square to the power of 1 by 3 minus Re. This is the format of height of the satellite. We are not going to derive much beyond, like it is just the same known formula. We are just trying to juggle the terms here and there and get this answer. So please don't try think it is such a big formula. No, you know this one, you can easily do this one. Just squaring it and then changing it, shifting terms here and there. Now, why did we derive this one? What is the reason for deriving this one? Height of an orbit. We wanted to know what is the height of an orbit for a geostationary satellite. Right? So there is a satellite called Geostationary Satellite. Please write down. Write down this part. So this is called this is the next topic. After orbital velocity, don't think it is orbital velocity itself. Orbital velocity is over now. But I'm going to go to the geostationary satellite. Okay. Now, when a satellite, right? Now suppose this is the orbit. And this is the Earth. Earth is already spinning. Earth spins in 24 hours. And you put a satellite here. And this satellite also goes around the surface of Earth, around this orbit, in the same 24 hours. That means, what does it mean? You have put this one above India means it is just facing India all the time. India turns there because of the rotation of this Earth, spinning of the Earth. This also goes there. This also goes there. And it goes on coming back to the same thing. So all the time it has to keep on looking at the same part of the Earth. That satellite is called Geostationary Satellite. You just look above, you will see a satellite always following you in the same part of the Earth. That means the time period of orbit should be 24 hours. That is called geostationary satellite. A satellite which is kept in such a way that it faces the same part of the Earth throughout the time. That satellite is called geostationary satellite. Right? Now, you can turn to this book. Look at the turn to this book. You find geostationary satellite and polar satellite. So, what are the conditions there? The conditions are, few of the conditions are there. How it will be revolving. First of all is, the time period should be 24 hours. Exactly equal to the time period of the spinning of the Earth. There are some conditions for geostationary satellite. The conditions are, angular velocity of the satellite should be same as that of the Earth. The same velocity of spin, and this also should be same. But look at this one. The direction of rotation of the satellite should be same as that of the Earth. Earth is also going from west to east. This also should go to west to east. It is not that this is going opposite. Cannot be possible. Right? It should be the same. Direction should be the same velocity. The orbital plane of the satellite should be coplanar with the equatorial plane. It should go along the equator, not in something else. That's not possible. It's along this one. It is also called as parking orbit. You have parked it exactly at the same place, and it looks like it is just parked, just be ahead. So that's a way. So when you look at the same formula here, so we already seen the formula about the height of the orbit there. So what is the height of this one? So we know height is going to be equal to, take a look on that same height formula. So it is going to be equal to T square G R E square upon 4 pi square minus R E. This is the height of the formula just before you have derived. Okay, in this one, okay, here T is going to be equal to 24 hours. What is 24? 24 into 60 into 60. This is the T. We want to know the height. RE, you know. Alright. G is going to be equal to 9.8 meter per second square. RE is going to be equal to 6.4 into 10 to the power of 3 meters. And then rest everything same. Putting this value, you will get height is going to be equal to, the height will be equal to, you get here as 36,000 kilometers. You will get a height of 36,000 kilometers. Look at this one. It is such a high height. The radius of the orbit itself is only, how much is the radius? The radius of the Earth is 6,400 kilometers. So above this one, exactly R you go, another 6,400, another 6,400, one more 6,400, another 6,400. You can keep on going ahead, multiple of 6 times. It almost goes 6 times, 5.5 times. You go there, then it is going to be the geostationary orbit. It is pretty high distance. In that height, when you put a satellite, that is called geostationary satellite. All the cricket match that you are watching, it's all geostationary satellite. All the telephonic conversation that you have, Idea, Airtel, everything, everybody is sharing a space in the satellite. And it all goes to there and comes back. If that geostationary satellite is not there, it is not possible. So that's a very, very good thing. India has launched several satellites in the top of it to keep on watching every action. So it is such a beautiful thing of this one. Alright. In order to see the total distance from the center of the Earth, if it is wanted to know height plus RE, if it is small r, is going to be equal to 36,000 plus 6,400. So you will get here somewhere around 42,200 kilometers. So it's going to be quite a lot of this one you will get, right? So I hope you got an idea about how much beautiful and wonderful it is to see a satellite above their surface. Now there's one more satellite called polar satellite. What is a polar satellite? Polar satellite belongs to another class of satellites. They are low altitude satellites. They orbit the poles of the Earth in north-south direction, whereas the Earth spins in its own axis in an east-west direction. Hence, a polar satellite can scan the whole surface of the Earth. So it will be orbiting exactly on the pole. From pole to pole it will go. Just first the North Pole and then it will go to South Pole and goes above. So, and because Earth is also spinning, so it keep on revolving around it. It will keep on capturing every segment of this one. It will calculate. So the height of the polar satellite is comparatively smaller, 500 to 800 kilometers only. A camera fixed on it can view small strip of Earth in one orbit, adjacent strip in the next orbit. Thus the whole Earth can be viewed strip by strip. The satellite used for monitoring weather, environment and all things. So that is the way it is. Polar satellites also usually it orbits in this thing. It orbits in 90 minutes. It goes and comes back. So that is the way polar satellites. I want to still make you to understand how the polar satellites works. This is the spinning of the Earth. So polar satellite will start here and go around this one and come back. So Earth is already spinning. This spin is already going on. So it goes, it will cover one strip. It will cover the next strip of the Earth, and then next strip of the Earth it will keep on covering. So the polar satellite, because Earth is spinning already, as the polar satellite is there, this one will go here now and it will keep on tracing this part. And again, after some time, this will be the Earth, will be in this facing the satellite, and it will capture that one. After some time, this part will be here, and this will capture it like this. So it will go on capturing it. Alright, there are a few topics which is optional. I'm just leaving it here. So whenever the Earth is having the satellite launched, it goes like this, and again it goes to a circular orbit, and it goes in the elliptical orbit, and then it goes beyond. So there's an option how the satellite is launched, that is given. It is optional. And weightlessness, it's also optional. I'm not doing it. So energy of the orbit, that's the binding energy is there, it's also optional. We're not doing it. With that it gets over. Then we'll go to the numericals. Alright children, thank you. Please read this one, try to understand. A very important derivation we have done. Thank you.